Molten rock flows beneath the ground, 900 degrees Celsius. Above it, the ground is frozen solid. The same island. And this island produces so much electricity, there's no one left to use it. Just 1,200 kilometers away, millions of homes pay soaring heating bills to stay warm through the coldest winter nights. In reality, each side holds the solution to the other's problem, and the idea is completely possible within the laws of physics. Yet after all these years, it still hasn't happened. Why? Most winters, your electricity bill gets a little higher. And more often than not, it's not because of how much energy you used. It's because of where that electricity comes from. A large share of Europe's electricity still depends on energy sources whose prices can change because of a war on the other side of the world, a pipeline agreement, or even the route of a single tanker. When the wind blows or the sun shines, electricity becomes cheaper. When the weather turns calm, prices climb again. Consumers aren't the only ones who notice these swings, but they're the ones who feel the consequences the most. Far to the north, across the ocean, the situation is completely different. In Iceland, the heat beneath the ground never stops. It doesn't depend on the seasons. It isn't affected by wars. Whether the wind blows or not, whether the sun shines or not, it keeps producing energy day and night, summer and winter, with the same steady reliability. The problem is that there's nowhere to use all of that reliable energy. The island's population is small, and its industry is limited. As a result, part of the energy it produces simply stays beneath the ground, with nowhere to go. On one side is a system that's volatile, expensive, and dependent on external factors. On the other is a steady, affordable source of energy that remains underused. So, could a single cable stretching 1,200 kilometers between them really change the winter heating bills of millions of homes? Here's the remarkable part. It's actually possible to transmit Iceland's surplus geothermal energy to Europe through a cable laid across the ocean floor. This project hasn't been built yet, but feasibility studies have already outlined, in considerable detail, what such a connection could look like if it ever becomes reality. The cable would stretch somewhere between 1,000 and 1,200 kilometers. Today, the longest operational subsea power cable is NorNed, the connection between Norway and the Netherlands, commissioned in 2008 at roughly 580 kilometers. This proposed cable would nearly double that record. And it's not just about the distance. Its planned capacity is equally ambitious, between 800 and 1,200 megawatts, a single transmission line capable of supplying enough electricity to power the cities of a medium-sized country. Nearly all of that electricity would come from geothermal heat beneath the Earth's surface and Iceland's abundant hydropower. Compared with fossil fuels, the carbon emissions would be extremely low, because geothermal energy doesn't rely on burning fuel. It taps into heat that's already there. The cable would become a river flowing beneath the ocean. But instead of carrying water, it would carry a silent, steady stream of energy. So, can we actually build it? From an engineering perspective, the answer is largely yes. But that yes isn't as simple as it sounds. In the next chapters, we'll explore what lies behind that answer, and why, at every layer, it still comes with one important word. But if this cable were ever built, its most noticeable impact would probably happen in the middle of winter, without most people even realizing it.
Power grids become the most expensive when demand reaches its peak, on a freezing evening, when millions of households switch on their heating at the same time. Under normal circumstances, utilities either bring fossil fuel backup plants online or buy expensive electricity from neighboring countries, and those extra costs eventually show up on people's bills. On a cold Tuesday evening, electricity prices can increase tenfold within just a few hours. But here's the interesting part. Iceland's electricity demand doesn't peak in winter. If anything, it rises slightly during the summer, driven by tourism. That means the periods of highest demand on each side almost never overlap. At the very moment Europe needs electricity the most, Iceland still has unused generating capacity sitting idle. On paper, it looks like a perfect match. And in many ways, it is. But for it to become more than just an idea on paper, one thing is still missing: the physical backbone capable of carrying that energy across the ocean. There's another side to this story, one that belongs to Iceland's own economy. Part of the island's energy production remains underutilized simply because there isn't a market to sell it to. If an export connection were built, that idle capacity could become a new source of revenue that could support new power plants, new industries, and new jobs. For Iceland, it could become an opportunity that has been discussed for decades, yet never fully set in motion. And there's one more potential benefit: Europe's energy mix. Much of the continent's renewable electricity comes from wind and solar power, both dependent on the weather, and both capable of dropping dramatically at the same time. In recent years, Europe has experienced periods of unusually calm weather, when wind turbines produced very little and solar panels couldn't make up the difference. Geothermal power from Iceland wouldn't eliminate that problem, but it could help stabilize the system. A constant, year-round source of electricity could provide balance alongside resources that naturally fluctuate. Electricity isn't just a commodity here. It's a rhythm connecting two very different parts of the world. And that rhythm depends on a far more delicate balance than it first appears. So, could this cable really be laid across the ocean floor? Or would the idea collapse the moment it meets the sea? With all this evidence on the table, why is the project still sitting on the shelf? The short answer is money. More specifically, the timing of the investment. The teams that seriously evaluated this concept stepped away from the project in 2019. The reason wasn't technical. As with many large-scale engineering projects, the real challenge was financing. We'll get into the details in a moment, because this wasn't a simple rejection. To understand why the project stalled and why it's attracting attention again today, we need to look beyond the price tag. Let's start with the depth. The proposed route would descend to around 1,000 meters beneath the ocean surface. That's not the deepest point ever reached in marine engineering, but for a high-voltage power cable, it means dealing with immense pressure and complex thermal conditions. The solution isn't new. Similar technology was already proven with the Norned interconnector between Norway and the Netherlands, which entered service in 2008. It has operated reliably for well over a decade. The North Sea Link, commissioned between Norway and the United Kingdom in 2021, follows the same fundamental principle. So depth isn't an unknown, it's a calculated engineering risk. But an even bigger challenge than depth is capacity. For this cable to operate at full capacity, Iceland would need to increase its current electricity generation by roughly 30%. That means building new geothermal and hydropower plants, securing new investment, and completing extensive environmental assessments. None of that is cheap, and none of it happens quickly. Unlike building a conventional natural gas or nuclear power plant, developing geothermal resources requires extensive exploration. Until test drilling begins, there's no reliable way to know exactly how much energy a potential site can produce. Beyond the engineering challenges, there's a third layer: political and economic uncertainty. For years, this project was described as something that could happen within the next few years. But each time, the timeline slipped. An assessment published in 2019 concluded that, under the market conditions of the time, the cable wasn't economically competitive. Energy prices, construction costs, and political priorities simply no longer aligned. But that balance has changed. In recent years, Europe's approach to energy security has shifted dramatically. The pressure to reduce dependence on fossil fuels is far stronger today than it was just a few years ago. The same economic calculation, under different conditions, can lead to a very different conclusion. The obstacles are still real, but they no longer carry the same weight. So how are engineers trying to overcome these three challenges? Before the cable is ever lowered into the sea, It would sit stretched across the deck, like a giant spool, extending for kilometers, black, wet, and surprisingly heavy. Cut through it, and you'd find layers of engineering, a copper conductor at its core, insulating materials, steel armor, and a waterproof outer sheath. Every layer exists to solve a different problem. A transmission line of this scale would have to use high-voltage direct current, or HVDC. Over distances like this, alternating current would lose too much energy along the way. Direct current keeps those losses much lower. But it comes at a price. Massive converter stations are required at both ends of the cable. One would stand on the edge of a volcanic plain in Iceland. The other, on a mist-covered hillside, somewhere along the coast of northern Europe. Each one would cover an area roughly the size of 3 football fields. These converter stations don't just switch electricity between alternating current and direct current. They also stabilize the grid frequency. Even so, about 3% of the energy is lost during the conversion process. That may sound like a small number, but by the time the electricity has traveled 1,200 kilometers, those losses become significant. Exactly how to minimize those losses remains an engineering challenge that hasn't been completely solved. The ships that lay these cables move at only a few kilometers per hour. Slow, patient, almost meditative. And that pace is intentional. The cable has to settle onto the seabed at exactly the right angle and under precisely the right amount of tension. A single mistake could mean recovering and relaying a cable worth millions of euros. The seafloor is a world of its own. Rocky outcrops, thick layers of sediment. In some areas, even abandoned military equipment from decades ago. Every one of those factors influences the route. The final path hasn't been decided yet. The landing point will depend on detailed geological and environmental studies. Before reaching the shoreline, the last few hundred meters of the cable would need to be protected inside specially designed conduits to shield it from waves and fishing activity. That last mile may sound like a minor detail, but it can consume as much as 10% of the entire project budget. And even a small change in the route can ripple through the entire project. The longer the cable becomes, the cost of installation doesn't simply rise in a straight line, it accelerates. So who would actually lay this cable on the ocean floor? Worldwide, fewer than a handful of vessels are capable of installing a subsea power cable of this length and weight. And most of them are already committed to the growing number of offshore wind projects connecting Europe and Asia. So, even if every technical challenge were solved, securing the right installation vessel would become a challenge of its own. The factories that manufacture cables of this scale face a similar constraint. They don't open production lines without orders placed years in advance. Then there's the question of money. Studies suggest that interconnectors like this, not just this proposal, but similar cross-border transmission projects as a whole, could save European consumers around £1 billion every year. The reason is straightforward. In many cases, importing electricity from existing low-cost generation is cheaper than building and operating new backup power plants locally. You would never see Iceland listed on your electricity bill, but its absence could be one of the reasons the number at the bottom is lower. Yet this cable is about more than metal and money. It's a bridge between two societies. Most people in Iceland rarely think about how rich their island is in energy. Heat has flowed into their homes through geothermal pipelines for generations. Opening the grid to the outside world wouldn't feel like a dramatic victory. It would simply be the next logical step. Across the sea, the perspective is different. European consumers won't simply assume that the electricity at the other end of the cable will arrive, or that, if it does, prices will actually fall. The same cable. Two very different meanings. For one side, it's an export. For the other, it's security. And then there's the final layer, the environment. Elsewhere in the world, another subsea interconnector of comparable scale is being planned in the Mediterranean, linking power systems that still rely heavily on natural gas. That project extends the infrastructure of the fossil fuel era. This proposal moves in the opposite direction. Nearly all of the electricity it would carry comes from renewable sources. heat rising from deep beneath the earth, and water flowing down from the highlands, not fossil fuels. The same engineering language, two very different futures. One extends the energy system of the past. The other could become a proving ground for the energy system of the future. And this is where all the pieces come together. If this project were ever built, humanity would, for the first time, deliver the heat from the heart of a volcanic island directly into the electrical grid of an entire continent. That wouldn't simply push the boundaries of electrical engineering. It would redefine the geography of energy in a way that could never be undone. If this interconnector is ever built, everyday life would probably change quietly, not through a dramatic inauguration, but through a gradual shift that most people would never notice. On the coldest night of winter, someone switching on the heat in a home somewhere in Europe could be using electricity generated thousands of kilometers away from the geothermal heat beneath Iceland's surface. And no one would think twice about it, because not being noticed would be the greatest measure of success. At their best, power grids are invisible. The outlet works. The lights come on. No questions are asked. In Iceland, the change could be more visible. If today's unused generating capacity became a source of export revenue, it could help finance new investments, new industries, and new opportunities. Scenarios in which electricity exports attract additional data centers or green hydrogen facilities are still very much part of the discussion. But the biggest impact might happen somewhere else entirely. If this idea proves successful, other islands with significant geothermal or volcanic potential could begin looking at the same model. Cape Verde, the Azores, even parts of the Pacific. This wouldn't just be the story of a single cable. It would be the first demonstration of a much bigger idea. So if that experiment succeeds, which island will be the next to answer the call? A force beneath the earth, one humanity can never truly control, hot enough to melt solid rock, could one day travel beneath an ocean and become the electricity that boils someone's kettle thousands of kilometers away. It would bring nature's most primitive power together with one of our most advanced pieces of infrastructure. And in the end, this isn't just about a cable. It's about the foundations on which the next era of energy could be built. The age of fossil fuels was built on extracting resources and transporting them across the world. This new model could be built on leaving the resources where they are and transporting only the energy. The difference isn't just a cable. It's a completely different way of thinking. That steaming ground, the smell of sulfur from the very first moment. Maybe the real question was there all along. Is it really possible not to tame such a force, but to trust it across 1,200 kilometers? Engineering says yes. Physics says yes. But do we? And this is where we reach the real question. If the idea is physically possible, economically promising, and environmentally compelling, why is it still sitting on the shelf? Maybe the real challenge was never technical. Maybe it has always been about trust. The hesitation to tie part of a continent's energy future to a single cable lying on the ocean floor. People will have different opinions on that. We'd love to hear yours. Do you think that hesitation is justified, or is the potential worth the risk? Share your thoughts in the comments. Maybe there's a perspective we haven't considered yet. As you're watching this video, the steam beneath Iceland's surface is still rising, waiting to be used. And there are projects even more ambitious than this one. In fact, some of the engineers working on them describe them as completely crazy. We'll explore them in our next documentary. Subscribe and turn on notifications so you don't miss it. Real problems, realistic solutions, AG projects.